Hello, everyone. Welcome to our talk. I'm Liz Lee from AMD. So today I'm so excited to talk about our latest work with colleague from AMD, Yanyuan, and from Meta, Matthias. So our topic today is efficient MoE pre-training at scale on AMD GPUs with TorchTitan. Huge thanks to all the contributors and collaborators from both AMD and Meta side. So here is our outline of today's talk. So Matthias will first introduce TorchTitan and also recap the concept of MoE models and the challenge of pre-training MoE models. Then I will dive into how we are going to accelerate MoE model training on AMD GPUs with TorchTitan. So we'll focus 3 areas: AMD GPU architecture advantage, and also our parallel strategy design, and our training kernel library, Primus Turbo. Then Yanyuan will focus on the performance of DeepSeek V3 Llama 4 pre-training upscale to 1K AMD GPUs by introducing our cluster setup, also the scaling chart test result. Okay, now let me hand over to Matthias.
Thank you very much, Liz. Hello, everybody. I'm Matthias from the PyTorch team, as Liz already mentioned, and I'm here to talk a bit about TorchTitan, which is our PyTorch native framework for large-scale training. And we developed TorchTitan basically to educate people, but also to show the best interests. But at the same time, we want to try to bring the best performance to the people and in people's hand. And we do this by making it very easy to use. So it's basically just a single configuration file where you have all the power to your disposal. And it just empowers researchers and developers to quickly iterate over different training configurations and adjust that to their environment that they have in front of them. And for example, all these parallelization techniques are integrated in TorchTitan. For example, pipeline parallel, expert parallel. You can just enable them with a single configuration line. Regarding model coverage, we are trying to keep it as broad as possible. So we have, for example, Llama 3 for dense models, and then for MoE models, we have Llama 4, and now we added DeepSeek V3 as well as the Qin 3 series. And we have Flux for image generation, and I think there is more to come in the future. So before we go into the challenges, I quickly want to talk about what MoE actually stands for. So it's a mixture of experts. When you go from a dense model like Llama 3 to a MoE model like Llama 4, what you replace is the big MLP layer after the self-attention. And we replace that with multiple MLPs, which are potentially smaller than the original dense layer. And then we have a routing element, basically, that decides which expert, which is the small MLP, gets to work on this token. Or it might be a subgroup of all the experts. And then there might be a shared expert. So, and that gives us the possibility to basically handle way larger models with more parameters. And while we are still staying within the same compute budget. So the computation will be the same, while the memory footprint can be way bigger. That's improving the training speed as well as the training accuracy, as we have seen in the last year. So to come to the challenges of pre-training and training MoE models in general, first of all, we have like the kernel efficiency. You can imagine that if you have a batch with multiple tokens and all of them get routed to different experts, you will end up having to call these expert kernels, basically, which is a matrix multiplication. And so that is very inefficient on GPUs. And what you want to do is you want to fuse these together. So you end up with something called a grouped general matrix multiplication that takes care of multiple experts in one kernel call. Then after the routing, basically, we have a communication step, because when we do large pre-trainings, we have like a large cluster with many nodes. So we apply expert parallelism. That means that we have different experts on different GPUs, and so we need to communicate these intermediate results of the token to these GPUs. So all the GPUs have to communicate in a big all-to-all communication, and that takes time. And so we try to mask that by overlapping it with compute, and also apply like shared memory techniques to make the communication as efficient as possible. And then there are composability issues with, for example, AMD found out that if you were just naively combining FSDP and pipeline parallelism together with expert parallelism, you ended up with a lot of pipeline bubbles. And a bubble means that you are not doing any work on a GPU in a pipeline stage at a given time. And that makes the training inefficient. So these have to get, we have to get rid of these to make the training efficient. And then there are like routing and stability issues that you can face where you basically have a routing collapse and you route all the tokens to a single expert, which makes your training inefficient, and also the accuracy will get worse. All right, so let's continue now with Liz and see how AMD solves these challenges. Thanks.
Thanks, Matthias. So yeah, as we know all the challenges of MoE pre-training, so let's look at how can we accelerate MoE pre-training challenges on AMD GPUs. So we will look into the 3 key contributing areas. The first one is AMD GPU architecture advantage. Second one is parallel design, parallel strategy design, and also we will introduce our new training kernel library, Primus Turbo. So AMD Instant MI300X is our leadership product and excel in large model pre-training and inference. So it's based on CDNA 3 architecture. It includes 256 gigabytes memory and also 6 terabytes per second memory bandwidth. In terms of compute, it includes 2.6 pflops FP8 performance and 1.3 pflops FP16 performance. So the big per GPU memory is super important for MoE pre-training because we can place a lot of experts locally on each GPUs. We can also run the higher capacities with lower token drop. So therefore, we can reduce the cross-node expert parallel communications significantly. Also, the FP8 and the BF16 matrix cores can further push our token throughput without exploiting the memory usage. Lastly, we have ROCm full stack is fully ready. We have communication libraries like Reso to provide collectives. We also have kernel libraries like Primus Turbo to accelerate the workload. So AMD GPU, we fully support multi-dimensional parallel strategy design. For example, we support both intranode and internode expert parallel. We support FSDP for data sharding. We also combine the pipeline parallel and virtual pipeline parallel to reduce the pipeline bubble. Together, we create a very efficient scaling strategy to enable the stable and large-scale MoE pre-training strategy. Oops. Okay, so Primus Turbo is our general-purpose kernel acceleration library for large-scale LM training on AMD ROCm. It's providing high performance, completeness, and ease of use. If we look at the diagram on the left side, in the front end, it supports multiple frameworks like PyTorch, and the JAX framework is coming. And for the component layer, we also support high-level building blocks like operators, modules, distributed primitives, and other kernels. So for the back end, we have all the support of important AMD compute and communication libraries like HipBlast, CK, AITER, Reso, Triton, and others. So Primus Turbo support a full range of AMD hardware, including MI325, MI355, and future MI450. So we want to make sure the portability of the performance across all our range of hardware. If we look at the right side, this is an example code inside Primus Turbo calling FP8 grouped GEMM, just in a few lines of code. So we only need to write like 2 lines of code in TorchTitan to call FP8 group GEMM in Primus Turbo. So this is really easy to integrate, really easy to use for everybody. Here is a table summarizing all the kernels we support in Primus Turbo. If we look at the table GEMM and group GEMM, we all support BF16, FP16. We support FP8 with tensor-wise, row-wise, and block-wise quantization. The FP6 and FP4 support is coming soon. Attention kernel, we support FP8 and FP16 and BF16. We also support FP8 with blockwise quantization. And deep EP, we support intranode and internode deep EP. We also support Mellanox NIC today, and the Broadcom NIC and AI NIC support is coming soon. All-to-all kernel, we support FP8 with tensor-wise and row-wise quantization. And we also support a lot of element-wise ops, including normalization, activation functions, swap, and so on. So this slide, we want to show a step-by-step perf optimization of DeepSeek V3 full-time pre-training run with Primus Turbo acceleration. If we look at this, this picture, so we use Torch Profiler to profile the workload first and identify all the key bottlenecks and hotspots with different kernels. Then we use the kernels in Primus Turbo to accelerate them. So the bar chart here is showing the per step optimization using the Primus Turbo kernels in a 64-node DeepSeek pre-training run. So in terms of throughput, we baseline as 100%. If we include enable AITER attention, the throughput can get up to 15%. Then if we enable FP8 GEMM, we get a huge performance boost, so 2x of the throughput. Then we enable FP8 grouped GEMM. It gives us like 277% compared to our baseline throughput. This is a demonstration of our Primus Turbo kernel's efficiency. So Primus Turbo also includes deep EP, which can accelerate the all-to-all performance significantly. Here we demonstrate the deep EP using a DeepSeek run. If we look at the curves here on the left side, in terms of throughput, we look at the red curve. The EP size is increasing from 8 to 16 to 32. We can see the total throughput is dropping a lot with EP size increasing. But if we enable deep EP with the blue curve, we can see the total throughput is almost identical even we increase EP size. On the right side, it's the all-to-all latency percentage of the total runtime. Similarly, for red curve, it's a normal without deep EP run. We can see with EP size equal to 32, the all-to-all latency is almost like 50% of the total runtime. But if we enable deep EP, the all-to-all latency will reduce like less than 20%. It's a huge like performance increase. Okay, with this, we want to show the pre-training performance scaling up to 1K GPU. So, Yanyuan, please.
Okay, so now I want to present our experiment results with TorchTitan to train DeepSeek V3 and Llama 4. And first, I want to talk about the experiment and the cluster setup, and then go through the results in detail. So for this MI325 cluster, And in total, we use up to 1,000 GPUs to run this workload. And this cluster is hosted in TensorWave. And for the NINC side, it's equipped with the Broadcom Thor-2 NINC. Bandwidth is about 400 gigabits per second, and the protocol is Rocky V2. So it's, the backend network is connected in a factory topology, which is typical used in the GPU cluster. So if we look at the DeepSeek V3 pre-training scaling results, so here we use the Docker, which AMD biweekly public release Docker. So you basically can find this one on the Docker Hub. And for the software side, we use TorchTitan and enable the Prime Turbo. So we enable those features, including the Torch compile, IP8 GEMM, IP8 group GEMM, AITER attention, and tune the parallel strategy based on our hardware features. So if we look at the right figure, the x-axis is the number of GPUs that we scale up, and y-axis is the training scaling efficiency. So if we put this the first setup as 100%, and if we further 4 times of the total number of GPUs, and we can achieve less than 4% drop. So I want to mention that the parallel strategy we use here is FSDP plus EP and PP and VPP. And we also tested other MoE models, which is Llama 4 Scout. So this model is relatively smaller than the DeepSeek V3, but still we can achieve very good linear scaling on this MoE training. Beyond that, we also check the numeric accuracy with our model training. So for this one, we use DeepSeek V3, and we enable the IP8 training. And for the dataset, we use LNAIC4, which is the public dataset from Hugging Face. For the learning rate, we picked the default value in the TorchTitan. We have it run for 900 iterations. So if you look at the figure, the x-axis is the number of steps, and y-axis is the loss curve. So basically, this training curve shows on this MI325 cluster, we can show the strong conversion curve with TorchTitan. So in conclusion, what we did is we achieved the near linear scaling with MoE pre-training at scale up to 1,000 AMD GPU. And we boost the training performance with our AMD open source training kernel libraries, Prime Turbo, and also the AITER and also Rico libraries. We fostered collaborations with Meta in this PyTorch open source ecosystem. So in next step, we will continue our optimization on the AMD libraries, including Prime Turbo, P-Blast, Rico, AITER, and CK. And we will continuously optimize the advanced MoE features, which is including the dual pipe. This is recently upstreamed in the TorchTitan, so we will continue working on to make sure this feature is fully enabled in our hardware. And next, we also want to support our next generation GPU architecture, which is MI450, and also our AI rack solutions. So finally, we want to expand our collaboration with broader open source projects, including the PyTorch Forge and PyTorch Monarch, which just released today. So finally, we have all the source code used in the project open sourced. We have those repo hosted in GitHub, and we also initiated the upstream effort to make sure all our optimizations can appear in the mainstream and the PyTorch community can directly use it. Okay, thanks to all the contributors and the collaborators for this work. So, and also thanks for the audience.
Thank you. Yeah, if you have any question, please ask us. We have 6 minutes.
Yes.
Testing.
Oh, do you have?
Oh, I had a question on the FP8 speedup slide with the. Oh, sorry.
Where?
Yeah, with the bar chart showing the speedup.
Bar chart.
I think if you go earlier a bit.
Bar chart.
bar chart, okay.
Yeah, this one.
Yeah, this one. I was wondering, it seems like you get almost a 2x from just the FP8 GEMM. I was just wondering if you can kind of go into a little bit more detail, because, yeah, just like, if the GEMM itself is a 2x, how do you get like an end-to-end 2x?
Go ahead.
Okay, so
I think the question is why we get FP8 GEMM performance up to like 2x.
Okay.
Yeah.
Okay, I can answer that question. So basically for the FP8 and by default, the TorchTitan will call the TorchAO library. Currently it has some quant like operators. And so those operators, like we found that it's not that efficiency, so, but with the Primus Turbo, we did some optimization on that. So beyond the pure FP8 GEMM kernel, we also optimize the quant part, so which makes sure that it can like achieve like around 2x performance boost. Yes.
I still have the same question. How well would it scale for 10,000 chips, and like what would be the performance?
10,000 chips. Okay, that's a really good question. So, I think for that one, actually, we can like break it down into like a multiple tiers, so like solutions. First is in the kernel level. We want to make sure that the kernel level is very efficient. Say, for example, for the FP8, we want to make sure like it can achieve the one that almost to the like a roof line. And another thing is the parallel strategy. For example, we just mentioned the DPEP, which is very helpful if we want to scale it to say from 1,000 to like a 10K or even larger cluster. So actually, also for example for the pipeline parallel strategy, we can also utilize the pipeline, how to optimize the pipeline to make sure like once we scale up, we will like have like a smaller time for the like a cross node communication or something like that.
Okay, and then yeah.
We wanted to maybe recreate the experiment on a small scale. Like without 1,000 GPUs, how would we do it? Maybe using the same like Docker.
Yes.
Yeah.
Yes. Okay. The question basically how to like reproduce the results with smaller cluster. I think in the results we show like say if we use say 256 GPUs, you can also like get some the results that we showed here. If we want if you have like a even smaller one, say you can even reduce the number of layers. But for example, for the DeepSeek 3, and you can reduce number of layers and then run it. Although it's not a full model, but you can still can see the performance boost by integrating our Primus Turbo. Yes.
Yeah. One thing to add is like even for DeepSeek V3 full model, we only need to use 16 nodes to run the full purge-training. So because of our memory advantage. Yeah, you can also reduce the layers of the DeepSeek model for smaller training. Yeah.
Really appreciate the DeepSeek results, but you mentioned also Llama and Flux. Did you have to change the parallelism strategy, or are the results consistent across those other models? I'm particularly curious about Flux.
Oh, do you mean the different model, like the Llama 3 model, the dense model? Oh yeah, I think we did. We also did the dense model pre-training at the beginning. Since this talk is more about MoE models, so we focus on the MoE models. But for dense model, we even have better scaling result. So yeah, we definitely can show you later in offline. But for like dense model, we have pure like linear scaling, and because Llama 3 like 70B, it's very small. It can fit just into one node. So yeah, that's no problem. Like we can tune the parallel strategy a little bit, but the result is super good. Yeah.
Hi, thank you very much for the talk. I really appreciate all the numbers and the tables. So my question is, with basically almost or more than 1,000 GPUs that you guys use to train the MoE models, what kind of specific routing or parallelism choices you guys had to make to achieve the linear scaling performance?
Oh, I think for that one, in the original DeepSeek paper, they use some auxiliary loss or some node limited routing for that. But for our case, we use first we use the EP8, which means that we don't need those node limited routing or something like that to do the routing. So other than that, we try to make sure it keeps the same as the original paper. Yeah.
Yeah, thanks for the talk. Wonder if you could comment on the MFU hardware utilization that was achieved on the GPUs during these large-scale training runs.
MFU, go ahead.
Oh, I think for these results, for this work, we want to show the step up that by integrating our kernel libraries. For now, we didn't including the absolute MFU number, but yes, so later on we will publish some tech blogs which including those numbers in detail.